So with this one, we're trying to find the expected value for all three of these scenarios, box A, B, and C. Now, we can figure out pretty quickly that we have two different outcomes for box A, which is getting $10. I'm not even writing yet, sorry. What I am writing isn't what I mean to. All right, here we go. So we've got $10 or we've got $100. So these are outcomes. And so the probability of these outcomes, we can see there's 4 and 1. So we have a 4 and 5 probability. So that gives us a 0.8 or 0.2. Now I'm going to do this quickly because if we go to the next one, this doesn't change. Because now we have 400 and 100, but really there's still a 0.8 probability of getting $10 and a 0.2 probability of getting $100 when you do that. So when you do the expected value for this, you can do this in your calculator. You could also just do 10 times 0.8, which is 8, and 100 times 0.2, which is 20. And when you add that up, you get $28. So $28, oops, that's not where I meant to put that. $28 is the expected value for A and for B. So those two are the same. The question is C the same? Now with box C, you have 1 as the expected value, and I'll call this Y. The probability of this is going to be 100%. So your expected value here for Y is going to be 1. So even though there's 28 $1 bills in there, your expected value is 1. No matter what you pull out, you're going to get $1. All right, so the answer is D, A or B, but not C.
Doesn't it say you can have all of box C? So wouldn't that be $28?
Gosh, I don't read things right. I never read things right. And this is why I would fail the AP test, and which is why I don't take it, but I try and get you guys ready. Yes, they all have the same expected winning. Okay, thank you so much for catching that. Okay. I feel like when I gave this bell work last semester, I actually knew the right answer and said it right, but then I kind of glanced over it too quickly now. Maybe this remote learning is getting to me. All right, let's move ahead. Thanks for catching that. So you can see we've got a number of things going on. And yeah, we're going to try and get through all this today. Really hope you read chapter 17 because the, is it 17? Whatever the second chapter is, I'm losing my mind. But anyways, this chapter about binomial and geometric probability, that will really help. But before we get started, I wanted to mention to you, I put in your grades for your progress checks. Remember, those are things that I expect you to finish. If you have not completed them, it's a 0 right now. But the good thing is, that sounds bad, and so your grades for the most part have dropped. But you will get full credit when you turn them in, so it will help your grade. So if you're looking right now and you see your grade went from wherever it was and now you just are freaking out, just do those progress checks, turn them in. I'm putting the zeros in now so that you don't get a 0 when you look at your final grade. And now this is kind of your reminder to get those done. Quarter 1 is going to end next Wednesday. You're probably aware of that. There's not going to be a midterm, and I'm sorry to disappoint you because we're just not going to have time. So the last grade that you're going to get is going to be your Unit 6 test on Monday. And this will be modified a little bit because you're just not going to have the time to do the test, me grade it, create a retake, you guys do the retake, and there's just not going to be the time for that. So I'm going to modify this Unit 6 test a little bit, and I will think about that tonight, and I will explain that more tomorrow. And I already have an idea of how that's going to be modified because I did the same thing last semester, except it ended up being our Unit 7 test. But when I say I'm going to modify this, I'm modifying it to make it less punitive if you don't do as well. The idea is that you will not get a really bad grade right at the end of the semester. Okay, so that's the hope. Okay, we are going to complete Unit 7 before spring break, but it's technically going to count toward next quarter. I don't think that they split up the quarters very evenly, so Fourth quarter is going to be quite long. So anyways, let's look at this binomial distribution. We already looked at this yesterday, and I'm not going to go into Tuesday we looked at this. I'm not going to go into great detail, but remember, we have we have a distribution of probabilities that will look almost like a normal curve, meaning that if you have a set number of trials, this is binomial. Remember, BINS is the operative acronym for us. And so the N means a set number of trials. And we might do like N equals 20 trials. Let's say 20. And there's a certain probability for success each time. Let's say we're dealing with a probability of 4. All right, we're going to get a distribution of outcomes that look something like this. And it will center, and we're going to see this today. It's going to center around 8, and we're going to get a certain standard deviation. We don't know exactly what that is. So you can get way more successes than 8. You could get up to 20 successes. You could get as few as 0 successes, but you're most likely to get about 8. Okay, so just to remind you what the binomial distribution kind of looks like, and it's good that it's normal, and technically it's not a smooth curve like this. That would be for continuous random variables, and this is discrete. But it's close enough to that, especially if our N is high enough, then we can still kind of think through it this way to some degree. So here's the whole idea. Here's what we're getting into first thing today. We can answer the question, what's the probability of getting up to X number of successes? And for that, we're going to use a specific function on our calculator, which is called the binomial cumulative distribution function, or cumulative density. I actually don't know. But anyways, the only thing that matters is binomial CDF. And then we also have the probability of getting exactly X number of successes. Now, we already did this on Tuesday. If you remember the scenarios we were looking at, it had a certain guy was driving to work, and what's the probability of him hitting a red light exactly 7 times out of 10? And we had a formula for that, which I'll remind you of real quick. The probability of your random variable equaling exactly a number is going to be N choose K times the probability of success raised to the K power times the probability of failure, represented by 1 minus P, to the N minus K power. And this is your formal definition, right, the formal formula for your binomial PDF. But now we can do this on our calculator, and I will show you how this is done. So this is the scenario I was talking about. And Pedro drives to work, 55% chance of a red light, 10 work days. Okay, we're good to go. Find the probability that the light is red on exactly 7 days. We already did this by hand. Now I'm going to show you on the calculator. And this is a distribution. And I showed you that it was a distribution that looked like this so that you can remember that, so that it'll help you remember that we go to the distributions menu. So if you hit second and variables on your calculator, we are already used to the normal CDF and inverse norm functions. But if you go down to the bottom, it's option A. You can find binomial PDF. And if you have the interface, you will see 3 options. It's going to say trials, P, and it's going to say X value. If you can't find that, raise your hand. But if I don't see any hands raised or anything, I will assume everyone's found that. So luckily, this interface does a good job of walking us through it. If you don't have it, you'll just need to remember that it's going to be, I'll write this again, trials, P, and X value. So that's what you're going to need to put in if you don't have the interface. So anyways, we've got, in this case, 10 trials, 10 days worth of driving to work. P, of course, here is going to mean the probability of success. And there's a 0.55 probability. So I'm going to put in 0.55. Let me show what that looks like. And then the X value, if we want exactly 7 days, then I'm just going to put in 7 right here. You might or might not remember the answer that we came up with the other day, but when we do this, we can see that this is about a 16.6% probability. So if you do remember what we came up with, it was that number. But now the calculator does it for us using that formula. And we can do PDF by hand with that formula if we had to. CDF is the cumulative distribution function. So I'm going to go ahead and erase this. Hopefully everyone's good with this. We're going to do some more examples, of course. But, okay, I already kind of walked through this. And that's what, okay, I don't need to show this. So Matt, I know that you have to put it in by hand. So let me know if you have any trouble with that, but that's what it should look like in your calculator before you hit enter. Okay, it said domain error. And I just remembered Matt is not here right now. We will have to look at that. I'm not sure what went wrong there. I don't recall seeing a domain error. Let's just move ahead, and in a minute, if we have some time, I will look into that with you. Okay, so we're going to take the same scenario, except now we're going to figure out what's the probability that the light is red on no more than 6 days. So what we're saying here is, what is the probability that we have a red light for 0 days, or 1 day, or 2 days, or 3 days, or 4, 5, or 6, but not 7, 8, 9, or 10. Oops. So we don't want any of those, but any of the others work. We can solve this a really slow and laborious way. If we did this by hand, I could do the PDF function and figure out the probability of getting 0. And then I could figure out the probability of getting 1 and all these. And then once I have all those, then I could just add all these numbers up and get the sum of that. You can imagine that takes forever. It is not worth our time to do that. So luckily our calculator has another function, which is binomial CDF. And so if you go back into your distributions menu, this is going to be option B. Okay, so again, we have trials. So trials is still going to be 10. We still have a probability of 0.55. And the X value here is the number of successes up to which we're interested in. So we want to find out the probability that there's red on no more than 6 days. So our X value here is going to be 6. And we can see when we do that, now if I had to plug this in without an interface, I would have 10 trials, 0.55, and then 6. And the answer we get, 0.734, basically. So there's essentially a 73% probability that out of 10 days, we're not going to see a red light more than 6 of those days. That's the glass half full side. The glass half empty says there's a 27% chance we're going to see red 7 or more days. So there we go. So remember, what this is saying is this is the combined probability of getting 0, 1, 2, 3, 4, 5, or 6 successes out of 10. And we're still using what we call Bernoulli trials because it is binary. We either see a red light or we don't. It's independent. One day doesn't impact the next, especially when it's randomly chosen. It is the same probability each day, 55% chance. And so the other thing that we add in here is that we have a set number of trials. Okay, so now we can answer almost all of these. We can't quite answer all of them yet. I never did in the poll, so I just did that now. Okay, so if we're looking at this, we have a few of these problems we can answer. Now, the ones that we can't, I'll go ahead and tell you, we're not going to look at A and C right now. We'll look at those later. But we can look at the remaining ones. What's the probability she misses the bullseye at least once? Okay. So this is another way of saying, what's the probability that she doesn't get 10 successes? And we can figure this out a lot of different ways, but I want to think of this as, what's the probability that she gets anywhere from 0 to 9 successes out of 10? So the only way we fail at this condition is if she hits the bullseye 10 times. So I'll ask you guys, which function should we use? Binomial PDF or binomial CDF?
CDF.
All right, CDF. And there is a way of solving this with PDF, and maybe we'll talk about that. But if I use binomial CDF, how many trials are we looking at? I'm sorry, I was saying 10. How many trials are we actually using here?
6.
6, there we go. I assumed it was 10 arrows. And that's what I get for not reading before I start talking. So it's 6 trials. The probability of success is what?
0.8.
0.8. And up to how many successes are we interested in?
9.
Well, since it's 6 arrows, 5.
Oh, then yeah, 5.
Yeah. Yeah, had it been 10, yeah, you would have been right. So there we go. That's what we're doing. Of course, you have your interface to kind of do that for you. So I'm putting it in. You already probably have the answer.
Real quick, could you run through how to get there on your calculator one more time?
Sure. You hit second and the variables button, which is by your arrows. So it says in blue, you'll see the distribution menu.
Yeah.
So second and then distribution, and you'll have to scroll down until you get to option B.
Got you.
Or you can also, it's a little faster if you go up because it's really close to the bottom of the list.
Yeah, I see. All right, cool.
Okay, so there we go. What's our probability here? You can just shout it out or you can write it, your choice.
What was the question?
I was just asking, what is the actual probability of missing at least once?
0.738.
There it is, 0.738. Okay. Now, there was an alternate way we could do this, and maybe for some of you, this is maybe how you thought through it in your head. And as long as you realize there's multiple ways of getting this done, and there are multiple valid ways of doing this, you might have realized the only way of failing at this scenario is if she hits all 6 of them. So what if I just did 1 minus the exact probability, or the probability that she hits exactly 6 of them? So this would be another thing. You can put that in your calculator if you want. If you do, you will find that we get the same answer here. Right? It rounds a little bit differently for different reasons, but it's far beyond the level of precision that we care about. So you get the same answer that way. All right, let's not spend too long on any one particular problem. So I'll do maybe let's see, how about this one? I'm just gonna do E and I'm gonna skip D and F. If you have more questions, we can come back to this. What's the probability she gets at least 4 bullseyes? So think on that one. What do you think we need to do here? And as you're thinking about this, to guide your thinking, I want to remind you that the CDF function, it's cumulative, but it always starts, if here's your binomial distribution of outcomes, it's always going to start down here at 0 successes and work its way to the right. All right, so it's always going to go left to right. All right.
Is it just CDF 6.84?
6.84. You are on the right track. You have the right kind of thinking. I'll tell you that CDF will come into play. So if we're looking at the possible successes right here, right? She could get 0 up to 6 bullseyes. And we want to find out that she gets at least 4. So the only outcomes that we're interested in are these 3, right? Now, if I did binomial CDF, if we did what you just threw out there, which it was some good thinking, 6.84. What that's going to do is it's going to give me the combined probability of these outcomes, left to right. So I don't want that probability. But what could I do instead?
Would you just put that in that's already there and do 1 minus that?
You're very close, very, very close. So if I did 1 minus this, that would be, let me erase real quick. That would be erasing all of these outcomes from, remember, this represents the full probability. That all adds up to 100%. So if I get rid of these, then what I'm left with is just the combined probability of getting 5 and 6. So it's not going to be that exactly. What change could I make?
Switch the 4 to a 3.
Switch the 4 to a 3, and there we go. So now if we do that, then I will, okay, if I can change this just a little bit, I'll just add this back. So now I will get all of these cumulative, and then I will subtract that away from 1, and that'll give me the probability of getting 4, 5, or 6. All right, so that's what my function is going to look like right here. All right. Go ahead, put in your probability of that happening. Okay. So there it is. All right. So this distribution will have a mean and a standard deviation. I kind of talked about that already, and now we're going to come back to it. So the mean of the binomial distribution is going to be fairly intuitive. If we have 20 trials with a 10% probability of success, you would probably assume that if you did this over and over and over again, you'd get about 2 successes, because 20 times 10% is 2. And luckily, that's exactly how we get the mean. So this is on your formula sheet for the AP formula sheet. And it's pretty straightforward. N here represents, of course, your number of trials. All right, and then P is the probability of success. So I won't write that out. But that's a number of trials times the probability of success means you'd expect to get about that many successes. All right, standard deviation is not as intuitive, but I will direct you to the math box on page 394, because it does give a good description and it does explain where this comes from, but it's not something that's going to matter to us. So here it is. The standard deviation of a binomial distribution, and you do not have to have this memorized, okay? If I throw out formulas and you're like, that's a lot of formulas, you never have to have these memorized. Almost never. I will say the z-score formula is not on your formula sheet, so you will want to remember that one. But anyways, this one is definitely on your formula sheet, and you can refer back to this, the formula sheet, as much as you need to. Now, your textbook does use Q. So if you look in your textbook, it's going to say the square root of n times p times q. I personally am not a fan of that, because it just introduces another variable, and that's just going to make some people think like, wait, what does q mean? Where's q? What are they talking about? But if you just say 1 minus p, then it's less to keep track of. Plus, the AP formula sheet uses this form of the formula. So we just take our number of trials, multiply it by the probability of success, multiply that by the probability of failure, and then you take that product and take the square root of it. Pretty straightforward. And again, we don't need to derive where that comes from, and we don't need to calculate it we don't need to worry about that part of it. Okay, so consider the same archer, 0.8 probability of success. And I think in exercise 18, there are 10 trials. So how many bullseyes do you expect her to get? So this is another way of saying her expected value is going to be the mean of this random variable. And we just found that's n times p. So how many bullseyes would you expect her to get?
8.
8. There we go. Just 10 times 0.8. And now you'll need to plug this number in, but you can do the standard deviation of this. You'll have to use your calculator here. You can put your answer down as soon as you find that. There it is, 1.26. So we would, if we wanted to create the distribution, we can kind of visualize what this distribution would look like. She could get as few as 0, as much as 10 successes. Here's 8 approximately. So we're going to expect to see the peak of this right here. Now it's going to go down to 10, right? And it's going to go down to 0. So this is going to be skewed a little bit. And we'll talk about the skew of the binomial as part of class today. But we expect the mean. I know the mean is going to be right here. So, and then the standard deviation, 1.26. So this is not symmetric, but we will look at this. We'll get into that part of it more later. We're not going to worry about part C yet. We haven't talked about that. Okay. So never mind. Let's just skip over that part. If you want more help with that, it's really just plugging numbers into a formula. So I'm going to assume that we're good with that part of it. All right, let's look at something right here. You can see at the top, we're talking about the 10% rule, but we're going to look at this experimentally first. All right, so if we have 100 colored coins in a bag, and you can see the 4 colors, you pull 5 coins with replacement. What's the probability that all of them are not green? And I want to do this somewhat fast. So with replacement, what's the probability for the first trial that it's not green?
%75%.
75%, so 0.75. And then if we are using replacement, so I pull a coin out, put it back in, what's the probability of the second time?
75.
Still.
There you go. Yeah, so this doesn't change, so we can kind of lay this out. So I'm going to say the probability of getting green, then green, then green, then green, then green one more time. Probably could have done this a little faster. Well, not really, but there we go. So if we just do that 0.75 to the 5th power. All right. I'm just going to put the answer down because this is really getting to a conceptual point. We're not focused so much on the math part of it right here. So there we go. There's about a 24% probability. Now let's do the same experiment, but without replacement. So we're going to pull a coin out, keep it out, and then draw from what remains in the bag. So what's the probability that all are not green? The first time it's still 75 out of 100, but then we do this again. And what's the next probability?
74.
Out of?
99.
99. All right, and just to finish this off, 73 out of 98, 72 out of 97, and 71 out of 96. So we can multiply this and figure out this probability. All right. And that's what I got. You can just double check that that's right, or that you got the same. So the point is, whether we use replacement or not, it's not that big of a difference here. I mean, is this less than 1% difference really going to throw off our probability that bad? No. I mean, in this scenario, it's not that big of a deal. There could be times where you need a really precise calculation, but here, close enough, right? We're going to do this one last time. And the only thing that's changed now between the second and third scenario is that now we're dealing with only 20 coins in the bag. So the probability of not getting a green the first time is still going to be 75%. In this case, it's 15 out of 20. But now every time, because we are not replacing, the next time is 14 out of 19, 13 out of 18. If you guys already have the numbers, you can start doing the math on your calculator already. So let's figure out what this probability is going to be. Okay, so that's what I got. And again, spending a lot of time on this isn't super important right now. The main takeaway is that if there was replacement, then we'd have a 24% probability of this happening. When we do the same experiment without replacement, it drops to 23%. We lost about a percent in accuracy. But if we were trying to do the same thing with a much smaller population, then not using replacement changed the probability by 4%, over 4%, which is probably enough where we don't consider that accurate anymore. It's not good enough. So this leads us to, we're using this to lead us to what we call the 10% rule. Okay. Almost always we're sampling from a population without replacement. Anytime you're randomly selecting people to participate or randomly selecting objects from a pool of objects, if you're like in a manufacturing line, you're sampling without replacement. If we were concerned with 100% accuracy for our probabilities and our results based on this sampling, then we would need some really complex calculations, which, this is just a fun thing, is called hypergeometric distribution. And we don't need to care about that, but we can know that it exists and feel happy about that. Okay, so we can compromise. So if we're sampling without replacement, as long as we're not sampling more than 10% of the population, we can treat it as though it was sampling with replacement. So the results that we get are not 100% accurate, but it's close enough that we can use the simpler calculations. So if I can make this really clear, the hypergeometric distribution is quite complex. And you have to have a lot of information for that, a lot more information. But your binomial distribution, and even, so if you're using binomial CDF, even if you're using your normal CDF, a lot of times we technically would want to be more precise if we want to get the 100% accurate answer, but it's way easier to use these two. And so as long as we don't sample more than 10% of the population, we consider that the probability has not been thrown off a great deal. So 10% is the cutoff. So there we go. We're allowed to use simpler math because the approximate answer won't be too far off from the true answer. Now this rule, I'm introducing it here. When we get to unit 9 is when we're going to see this 10% rule, and you will see it so much that it's just going to be like second nature. It's going to be one of the main takeaways that you remember from the stats class. All right. But I just want to emphasize the reason for the rule, and I'll keep emphasizing it throughout the course. With the 10% rule met, we can use simple math. If it's not met, technically we have to get more complex. So that's kind of 10% rule, and that was a conceptual idea. But now let's jump into our other type of distribution here, which is geometric probability. Okay, and I will tell you that binomial probability is used 90% of the time when it comes to AP, but you will still see questions related to the geometric probability, so we need to know about it. Okay. Maybe we're not looking at a set number of trials and saying, here's 10 trials, how many successes could we expect? Maybe we're saying, hey, here's this event that has an X% probability of happening. How long is it going to take until we actually see a success? And so the geometric probability helps us answer that. So if you remember the basketball player that we saw, he was a 72% free throw shooter. I, however, am less than a 72% free throw shooter. And we're going to be very kind and call me a 20% free throw shooter. And I honestly would be thrilled to say that I can make 20% of my free throws. But let's just go with it. So what is the probability that the first shot I make is on my 8th shot? Okay, we have a formula for this. This is also provided on your AP formula sheet. And let's just calculate this by hand. Now, maybe let's figure this out. Let's explain why this is the formula. So my 8th shot is when I finally make one, and I have a 20% chance of making it any given shot. So what I'm really saying was, what's a probability that I probably should have done something besides 8? But what's the probability that I miss and miss and miss and miss and miss and miss and miss, and then I make it? I think I counted that out right. So I missed 7 times, and then I made it the 8th shot. So that's just going to be the probability of missing. If 20% is a chance I make it, 0.8 is a chance that I miss it. And this is 7 times I miss it, times the probability that I make it is 0.2. And we can kind of see that's what's going on. This is the probability of failure times raised to the power of n minus 1. And then this is the probability of success. So we're saying let's fail X number of times minus 1, n number of times minus 1. And then that last one, let's succeed. So the formula itself does follow logically. So we can figure that out. I mean, not that we're particularly concerned with this scenario, but we could figure out the probability here. There's about a 4% chance that that's going to be our reality. Okay. And this, I know, if you had money riding on the fact that my 8th shot was going to be the first one I made, then you know you have about a 4% chance of that happening. All right. So this can be solved on the calculator. And so again, if you look at your distributions menu, so second and variables, if you found the binomial, CDF, and PDF, now you can see the geometric down at the very bottom. It says it's geomet, PDF, and CDF. We're going to look at the PDF first. So that's going to be option E. So this is going to calculate the probability of my first success being at exactly the Xth or whatever trial. So in our example, we would put in a probability of 0.2. This is still the probability of success. But in this case, I want to figure out the X values. Which shot is it going to be that I finally make my first one? 8 is my X value. And we can see the 0.0419. Oops, I wanted to go back. So on your screen, before you hit enter, geomet PDF. Oh, okay, and there's 0.2 and 8. So if you have to enter this in without the, I can think straight, the interface, so you just have an open parentheses, you'd put your probability of success and then which trial you are concerned with. Okay. So now we can answer all these questions. We actually already answered a couple of these, so let's look at these two. This Olympic archer is shooting 6 arrows. 80% of the time she gets a bullseye, so we're good with this. What's the probability that her first bullseye comes on the 3rd arrow? So you can just write the answer on the screen. I'll just put probability of this event happening. And then I'm going to ask you to explain how you found it. All right, so how did you get that answer?
I went to the geometric PDF and put 0.8 for P, and then 3 for the X value.
All right, PDF. Very good. So that was, oops, I didn't mean to do that. It was 0.8 and 3. There it is. Okay, now you can figure out the next one. And I don't think we need to talk through the next one, just see if you can come up with the answer. And so we'll look for this one. What's the answer going to be? Okay, 0.0077. So 8/10 essentially of a % chance that it takes her until the 4th or 5th. Now we don't know anything about the 6th here, but the 4th or 5th is when she gets her first bullseye. Was everyone able to come up with that, or does someone have questions on how we got to that point? Okay, people are good with that answer. Any questions though? Okay, so we could ask a different question, which is not so much what's the probability that she gets it on her 4th or 5th, but maybe it's, if we go back to me shooting free throws, not so much what's the probability that I make it on the 8th try exactly, but what's the probability that I don't make it before the 8th try? So this geometric is probably going to be, you're going to have to pause for questions on like this, and knowing how I can read things wrong and make simple mistakes, and you've seen that happen a few times. This is the kind of question where I have to sit there every single time, no matter how good I feel like I am with probability. I'd sit there and kind of think through every time, like, wait a second. For this example, do I need to do this, that, and just kind of work it through. So let's kind of work through, if I am not going to make my first free throw before the 8th try, that means the very first time it's okay for me to make it is on the 8th one. This is not the same as just taking the probability of hitting it the 8th try and then getting the complement. So it's not going to be that straightforward. Instead, what we can do is we can figure out the combined probability of what's the probability I hit on my first shot? What's the probability I hit on my 2nd, 3rd, 4th, all the way up through 7th? What's the probability for each one of those being the first time I hit it? And then taking the complement of that. And we can use geometric CDF. So again, it's cumulative. If you're going to get probabilities for multiple outcomes, that's cumulative. So that's what that C stands for, and that can help remind you. So I want to do a geometric CDF here. Let me see that next. So we can actually answer this real quick. So same as before, it's under your distributions menu, the very last option. Our probability that I make a shot is 0.2. And the X value in this case is now going to be 7, because we want the cumulative probability that any of the first through the 7th is the first one I make, and the 8th is the first one that I am allowed to. Okay, so if you're following along with the logic, let's just go ahead and calculate that real quick. I'm going to write this on screen so that whenever you check your work, you can double check. All right, geometric CDF. 0.2 is probability of success, probability that I make it anywhere between the 1st, 2nd, 3rd, 4th, 5th, 6th, and 7th. So is this our answer? So let me mention this to start off with. And sorry if I'm interrupting your thinking. There is a 100% chance that eventually I will hit a free throw. If you give me enough shots, I will eventually make one. So there is a 100% chance of me making it. What's the probability that I make it within my first 7 shots?
79.
79%. So I can just put the 0.79 right there. That's good enough. So the question asked was, what's the probability that the 8th is, or that I don't make a free throw before my 8th shot? So what do I need to do with this?
Subtract it from 1.
There you go. I will eventually make it. There's an almost 80% chance I'm going to make it in the first 7 shots. I think it's too high of a probability, but this is going to be 0.21. There is a 21% chance it's going to take me 8 or more shots to get that done. Now we already know there's about a 4.2% chance it's going to take me that I will get it exactly on my 8th try, but there is a 21% chance it could be 8th, 9th, 10th, 11th, 12th. And of course, since this goes on infinitely far, it could not be, I could shoot 1,000,000 times before I make it. I don't want to have to calculate every single probability out to 1,000,000. So the easy thing to do is figure out the probability from 1 to 7 and subtract it from 100%. All right. Are there questions on this? There it is. Now, I don't know if I have a spot for this. Before we answer this question, I wanted to show you, we already saw that the binomial distribution looks almost like a normal distribution, especially if we have enough trials. If n is pretty big, so if n is greater than or equal to like 100, then it's going to look like a normal distribution. But the geometric distribution has a very different look. It has a distribution like this. The reason being, we're saying, what's the probability that your first the first time you do something is the first time you succeed, and then the second, and then third, and then the fourth, and so on. Now, the probability that something is your first success exactly on the, if I zoom over here and say this is my 112th attempt, I mean, what's the probability I'm going to get it exactly on the 112th? it's not very high. So your highest probability is your very first time. So if you were trying to make a bet that said, I'm not very good at making this, if it's free throws, I'm not very good at free throw shooter. But if you're trying to bet when you're going to make your first one, and you're trying every time, then your best bet is to say, I'm going to make it my first try, because your odds never get better than that. Okay. That is different. They say you have to make it within your first 10 shots. I'm going to give you 10 tries. Anyways, I'm getting too much into the weeds with my talking. So suppose a computer chip manufacturer rejects 2% of the chips produced because they fail at pre-sale testing. All right, what's the probability that the 5th chip that you test is the first bad one you find? And what's the probability you find a bad one within the first 10 you examine? How about you guys just find the answers and then be ready to explain your answers? So we've got a couple answers on the screen. I'm going to pause for just a second so that everyone has a chance to kind of run through this on their own. And Kevin, I believe you put the first one up there. And if it wasn't you, it was someone else. But Kevin, if it was you, go ahead and explain how you came up with the first one.
I went to, hold on, geometric PDF and put 0.02 as a P and then 5 as the X value.
0.02 and 5. That's the probability of getting the first success, which in this case is a failure, funny enough. The first success at exactly the 5th. Okay, and for the next one, Lily, that was you, I believe. How did you come up with that?
I went to geometric CDF and then put 0.02 and 10.
And 10. Very good. There's no reason for us to stress out on the calculations for this stuff because the calculator makes this really simple. But the hard part, like you can see, is processing through which one of our distribution functions should we use? Is it binomial, PDF, CDF? Is it geometric, PDF, CDF? And once you've got that down, it's pretty straightforward, though there can be some complications. Okay, so one thing that we haven't talked about yet, I just said, hey, here's a geometric, the way that we solve it. But we need to kind of assess a question at the beginning to figure out if it's even appropriate to use the geometric PDF or CDF, geometric distribution. So we have an acronym for this one also. Now notice these are Bernoulli trials. So it must be a binary situation. We either succeed or fail. They have to be independent. We have to assume each one of those computer chips was independent of the other, which might or might not be a fair assumption. This is different. For geometric, we're looking for the first success. So be on the lookout for that kind of concept. Maybe they actually use the word the first success. Maybe they phrase it in a different way. And the same probability each trial. We have to assume every chip has a 2% probability of being rejected. So there it is. Instead of bins, N represented the number, we had set number of trials. But here, if asked, when is the first success? Then that's going to clue us in, okay, this is geometric, not binomial. And of course, like I said before, the B, I, and the S will always be there because we're looking at Bernoulli trials. So I'm not interested in the full problem here. Just read this and let's make sure it meets our criteria. Now, here's what you could do is you could say, is this BIFs or is it bins? All right, so, I mean, we have to check binary, independent, and same probability. So I'm just gonna kind of talk through this one. 8% of males are colorblind. A researcher needs some colorblind subjects for an experiment and begins checking potential subjects. All right, so someone is colorblind or they're not, so we're good with that. Independent, we have to assume each person does not have an impact on whether the next person is colorblind or not, so independent. Same probability. I would assume every male that comes through has an 8% chance. So it is Bernoulli trials. And now if we start looking at these questions, notice that I'm seeing the first colorblind man, that she finds someone. Now this one doesn't say first for the last question here, but basically what's the probability that she finds someone before the 10th? Well, the first one would be before the 10th. So that one is as well. So we're really looking at a situation where we're looking for the first success, and we don't have a set number of trials. Okay. So that's hopefully pretty good. We will come back to this question, but before we can kind of finish this, there's a couple of things here: the geometric mean and standard deviation for this distribution. So if you, now I already have this up on screen, but if you estimate your own free throw percentage or any percentage, whatever that number is for you, if you think you could hit it 50% of the time, I mean, good for you. If you think you have like a 10% chance of making one. So how many free throws do you think you'd need to take based on your free throw shooting percentage that you made for yourself? How many shots do you think you need to take on average until you made your first one? And I asked, how'd you come up with your answer? But I already have this on the screen. Now, oops. The idea here, and I think it's fairly intuitive, is that if I've got a 20% chance of making a shot, then I could just do 1 divided by that probability. And what this is saying is, when I calculate this, it's going to say it's going to take you about 5 shots until you get one. And you think, okay, well, 20% of 5 is 1. So we're getting the reciprocal of our probability. That'll tell us how many we might expect, how many shots until we get our first success. So this makes sense. If you have a 10% chance, and then you take the reciprocal of that, then you're going to get 10. So we would expect 10 shots until you get your first success. So it's a very straightforward formula, and hopefully a very straightforward concept as well. This, we are not going to worry about the derivation of this, but this is the formula, and this is the one that I will use. This is the formula for the standard deviation of a geometric distribution. And your book writes it this way, which I think is unnecessarily complicated. And again, they introduce another variable called Q, which is just the probability of failure, but they like to use that different number, that different variable. But I will always write it like this because that's how you'll see it on the AP test. And they are equivalent. So if you like one and you really want to use it, there's nothing wrong with that. All right. So as far as questions about the mean and the standard deviation, it's really as straightforward as, like, if it asks for it, just plug numbers into the formula and then spit out what the answer is. All right, so in this one, so we go back to this computer chip process, and it said, how many do you expect to test before finding a bad one? So it's just another way of saying, what is the mean for this random variable x? Because it's geometric, I'm going to do 1 over the probability, which is 1 over 0.02, which should be 50. There we go. So we would expect to test about 50 computer chips until we found our first bad one. And when we say it's the expected value, if we did this testing every single day, and we do, and we just keep track, like, oh, I tested 47 today before I found my first bad one. Today I tested 100 before I found my first bad one. And then today it was my second one. On average, it's going to be about the 50th chip that you check. Okay, now we could also get the standard deviation of this. So the standard deviation of this random variable, it doesn't ask for it, but it's going to be the square root of 1 minus p over p. So the probability of failure here is 98%. The probability of success is just 0.02. So we can do that easy enough. And I got 49.5%. Or not percent. That's not percent. I apologize. It's the standard deviation, so it's the same unit as before. It's going to be 49.5 chips for your standard deviation. So don't know if there's much more to say with that, but now we can answer this. And let's not do everything here. I'm just going to have you guys independently work on problems A and D. Okay, so if those are the answers, how do we get the first one? Anyone can speak up if you got the idea. Yeah.
I just did 1 divided by 0.08.
All right, this is just the mean of this random variable, which is 1 divided by 0.08. You got it. All right, the next one, what about that?
You do geometric CDF and then enter 0.08 for the P and 9 for the I don't remember what the other value is,
Yeah.
but you enter 9 for it.
Yeah, so it says X value. That just means basically the trial number, the event number in order. Yeah. So yeah, there we go. So what this means with the CDF is that any of the successes 1 through 9, and then all those probabilities added together is 52.8. So there's that probability that we're going to get a success in the first 9 people, which is before the 10th person. Very good, very good. All right, how much more torture am I going to subject you to today? I don't know. I think I might have skipped over a problem. No, I didn't. Large counts condition. I wanted to talk about this. I'm doing a lot today. I appreciate you guys hanging out, and I know it's not necessarily, this might be a lot of information getting thrown your way. So we're going to look at this real quick. We just learned how to find the mean and standard deviation of both geometric and binomial distributions. BIFS tells us it's geometric. BINS tells us it's binomial. Okay, we're going to focus on the binomial distribution. And I want to pull this up. Okay, so let's go to the archer who has a 0.8 probability of hitting the bullseye. And we can see on average, we would expect her to get, let's see, well, no, there's about a 39% chance she gets it. 5 successes out of 6. Okay, now this graph, you can see it is unimodal, but it is not symmetric, it is skewed. So if I had 20, I've used this example before, 20 with 0.4 is the probability. This is starting to look symmetric and unimodal without outliers. It's starting to look like a normal distribution. But, you know, maybe you still look at it, it's like, it's a little bit skewed to the right, maybe just barely. It's a little bit skewed to the right. And now maybe if we bump this up to 50, now, I mean, we probably don't have any doubts that this is fairly normal. And keep in mind, this does have a limited range. It only can go from 0 to 50 because either you have as low as 0 successes or as many as 50, but you can't go beyond that. So if I had now this 50 looks good, but what if I did a 0.1? Or let me do it even more than that, 0.01. So now look at that, 0.01, this is no longer a normal distribution. Just a second. Sorry about that, I had an alarm going off. So that's great, we have a lot of trials, but our probability is really low, so now it's very skewed again. Or of course, if I went up to like a 0.98 probability, then it would be skewed, but it'd be left skewed. So we have to figure out what is the criteria to determine if it is normal or not. Because if I went to a 0.6 probability, now it's normal again. So we do have a rule to help us figure out if a binomial distribution is approximately normal. All right, let me project this big again. So if we have enough trials, it will be approximately normal, and therefore we can use the normal model to find probabilities. But how many trials do we need? Well, we have this rule. It's called the large counts condition. Now, I think your book calls it the success failure condition, but you'll frequently just see it called large counts. Okay. And we want to make sure we have at least 10 successes and at least 10 failures. And yeah, so the upshot, the main takeaway is that we can just multiply our number of trials by the probability of success to find the expected number of successes. And multiplying n by 1 minus p will tell us the expected number of failures. And both of these numbers should be greater than or equal to 10. So there it is. This is straight from the book. And remember, Q means failure. So this is the large counts condition. All right. So this is the main reason for having the large counts test. If our data passes the large counts condition, then we can consider the distribution approximately normal. And that makes our calculations a little more straightforward. And again, this is kind of like the 10% condition. I'm throwing it out, introducing it right here. It is part of this chapter, but this is really going to come into play once we get into units 9 and beyond. We will be checking the 10% condition and the large counts condition quite frequently. And I will constantly remind you of this. All right. So if we just look at this, we want to test the conditions before we try and answer this question. And this one might be a little bit challenging, but an airline believing that 5% of passengers fail to show up for flights overbooks and sells more tickets than there are seats. Suppose a plane will hold 265 passengers and the airline sells 275 tickets. What's the probability the airline will not have enough seats, so someone gets bumped? Okay. So the first question is, does this meet the 10% condition? Do these 275 passengers, does this represent less than 10% of our possible passengers?
Yes.
Yeah. And the idea, just because this might seem a little weird, like why are we checking 10% on this? The idea is there might be a population of people who are notoriously late. And there might be a population of people who are notoriously on time. I would probably be in the late category myself, but not for plane flights. Anyways, we want to make sure that if these are like 275 people who bought tickets, if these are 275 random people from the population, is it a big enough population that we're not going to likely get a skewed representation? And yeah, we have such a huge population who could fly in a plane that 275 is nothing. It's barely a drop in the bucket. So we definitely are sampling, meeting the 10% condition. and we don't need to worry about the calculations being off by any significant amount. And the next one is the large counts. Before we start trying to figure out the probability of this, we want to figure out, can we model this with a normal calculation? And if we can, then, well, if we can use normal. Sorry, I was jumping ahead. But can we do that? We need to check the 5% condition. All right, so they sold 275 tickets. How many failures would we expect? Sorry, how many people so N times P. A success here is someone failing to show up. So that's going to be 275 tickets sold times 0.05. So that is 13.75. We would expect to have about 14 failures. Now, N times the probability of failure, this one really is kind of redundant to check. We know it's going to be good. That's 0.95. So this is going to be whatever's left over, but that is 261.25. So we can say that the large count condition was met. We can, first of all, use our simpler calculations because it met the 10% condition. And secondly, we can approximate this with a normal model because it met the large counts condition. Okay, and now we need to figure out the probability. What's the probability that the airline will not have enough seats? So there are 275 tickets, and I have to kind of think through this probability. 265, so we need how many people to not show up?
10.
We need at least 10 of these people to be no-shows. Okay. So what are we going to do here? What are we going to do? All right. So 275 and okay, so we need to find the average amount. Man, why my brain is lost right now. I'm trying to figure this probability out. And I'm not necessarily trying to keep you guys here past 2:30 to figure this out. So the main thing for this problem, I do want to go through this problem, but my brain is fried right now to try and figure that one out. But I will go over this one tomorrow. We are close to the time anyway, and I don't want to keep you here later. So why don't we push pause on that? We covered everything today, just barely. So the main thing, again, was just checking our conditions and getting you comfortable with that idea. So there we are. There's your homework tonight. We will go over that other problem tomorrow. But all right. If you have questions, and you very well might have questions, let me know. Remember that your grades are final for this quarter on Wednesday. So if you have questions on how to get those grades brought up, like test retakes or anything, you can stick around and ask questions like that too. I've kept you here long enough. Have a wonderful day. I will see you tomorrow.